This is Calculus Part 7. Back in Part 6 we were looking at the section modulus of a rectangular cross section. We found that section modulus Z is equal to base times depth squared over 6. This chart also tells us moment of inertia. Moment of inertia is defined as all these little increments of area times their distance to the centroid squared. So the moment of inertia divided by the y max gives you your section modulus. Well, y max is the distance between the centroid and the place where the maximum stress occurs. In this case, it's from there to there, which is depth over 2. Depth goes all the way from there to there, so from there to there would be depth over 2. So, as it says, depth over 2. That's what our y max is for this cross section, a rectangular cross section. So, section modulus is defined as moment of inertia divided by y max. So base times depth cubed over 12 divided by depth over 2 will give you base times depth squared over 6, which we have right there. So let's take a look. Here's our 2x4, our rectangular cross section. Let's look at this little sliver of area right there. Okay. It's W wide and it's DH high, and we know that DI, a little increment of moment of inertia, is equal to dA, which is the area of the sliver, W times DH, times the distance between the sliver and the centroid squared. Okay, so instead of dA, we'll write WDH, and let's not forget that h squared. So W is a constant, so we have DI equals W, a constant, times h squared DH. And what's the integral? Let's integrate this. The integral of dI is I. And what's the integral of h squared dH? Well, it's h cubed over 3. So we have W h cubed over 3. And we're integrating. Our limits of integration are from 0 to 1/2 capital H, 0.5 times capital H. Okay. So we plug in 0.5 times capital H there, and we'll get 0.5 times 0.5 times 0.5, that's 1/8. Times 1/8 capital H cubed over 3. Okay, well, 1/8 divided by 3 is 1/24. So I equals WH cubed over 24. But remember, all we figured was the moment of inertia for the top half of this board. The bottom half contributes just as much. So the whole I, we probably ought to just call this I 1/2, because that's only half of I. So I total equals twice that. Well, WH cubed over 24 times 2 is WH cubed over 12. And let's see, that's the same thing we had over on our picture here. Remember that? Instead of W we call it B, and instead of calling it H we call it depth. We said B times depth cubed over 12 was our moment of inertia. And here we go with it again. Same thing. That times that cubed over 12 is moment of inertia. And our y is our distance between our center line, our centroid, and the place, the top of the board where the maximum stress is. Y equals this big H over 2. So moment of inertia divided by y is section modulus. Let's just say section modulus z equals I over y, which is WH cubed over 12 divided by H over 2. Okay, well, H cubed over H is going to be H squared. Okay, and 12 times 1 over 2 is going to be 6. So there we go. Our section modulus, we have the same old formula. Base times the height squared over 6. Just like we had over here. Except we called it base times depth squared over 6. We can use calculus to determine the stress in a propeller shaft. See, here's a round shaft. There's a side of it going off there. We would attach the engine at one side, or a transmission at one side and propeller at the other end. Okay, obviously a propeller shaft that's bigger than it needs to be will add unnecessary weight to an airplane. And a propeller shaft that isn't as big as it needs to be may break and lose its propeller. So we want it to be the right size. The stress in a shaft, which results from a torque being applied to the shaft, is greater toward the outer surface. The stress is going to be greater out there than it will be toward the center. Okay, just as the wood at the top and bottom of a teeter-totter board is stressed more than the wood in the metal toward the outside, the metal out here, is stressed more than the metal at the center of our shaft, our propeller shaft. Okay, to calculate the torque that a shaft can withstand, we'll integrate the torques of an infinite number of rings from the center to the outer edge of the shaft. Okay, here's a incremental ring that I drew arbitrarily. As long as it's somewhere between the center and the outside, doesn't matter where, because we're going to integrate an infinite number of them from the center to the outside. We're saying the radius of the shaft is capital R, from the center out to there. And the radius of our little incremental sliver that we're looking at is lowercase r. And the thickness of our sliver, which is infinitely small, just barely above 0, we're going to call it dr. Okay, let's let dA equal our incremental ring's area. D, a little sliver of area. Okay, well, it's going to equal the circumference of the ring, which is 2 pi r. Okay, anytime you have a circle, whatever the diameter is, you multiply that times pi, which is 3.141592, and that's what your circumference will be. If that's 1 inch from there to there, that's 3.141592 inches around the circle. That's 1 mile from there to there. This is 3.141592 miles around it. So our little increment of area is going to be this circumference, which is pi times the diameter, but diameter is 2 times the radius, so pi times 2r. That's our circumference. Now our area is a circumference times dr. Okay, the incremental amount of torque that is attributed to this ring of area is equal to the area times the stress times the distance to the center of the shaft. The stress, S, is equal to stress here at the ring. You know, stress is going to vary from the center to the outer edge. The stress here at the ring is equal to maximum stress times this ratio of little r to capital R. Okay, the distance from the ring to the center of the shaft, from there to there, is just lowercase r. Therefore, we can say torque equals area times the stress. This little incremental amount of torque of our ring is equal to our incremental area, dA, times our stress there at the sliver, times the distance from the sliver to the center. So our little increment of torque, we'll call it dt. dt equals our area, dA, pi times 2r times dr, and 2 pi r dr. Okay. Times our stress, which is S max times little r over capital R. Okay, there's our area, there's our stress at the sliver, and our distance from the center to the sliver is just plain old lowercase r. So we now have, okay, let's move our constants over. We have 2 times pi times S max there's an r, there's a lowercase r, and there's another lowercase r, so we have lowercase r cubed. Okay, dr, and we have a capital R on the bottom, so let's put it down there. Now let's integrate both sides of this equation, with our limits of integration being r equals 0 and r equals capital R. Well, the integral of dt is t. Okay, the 2 pi S max over r, that just carries right on along. Okay, the integral of r cubed dr is r to the 4th over 4. Okay, and now if our limits of integration are from 0 to capital R, looks like we're running out of room here, we'll have to say t equals 2 pi S max times capital R to the 4th over 4 times capital R minus 2 pi times S max times 0 to the 4th over 4r, so we might as well just forget that. We can go ahead and throw that away now. Okay, and r to the 4th over r is r cubed, so torque equals pi times S max times r cubed over 2, because 2 over 4 is 2.